Welcome. Good morning, everyone. Hey. Nice to see you here. It's the first lecture of this morning, and maybe you're still a bit tired from yesterday evening. And today's lecture will be quite practical, I would say. So it's not a very theoretical lecture, and I hope I can activate you a little bit to think along and participate. We will have a break after 45 minutes to get some tea. I'm always in need of some tea halfway the lecture. Also, welcome everyone who is joining online. If you have any questions, type them in the chat and I will treat them also. My name is Suzan Verberne. I'm a professor of natural language processing at Leiden University. And my research is about information retrieval. And currently, a lot of that work has to do with the use of large language models for information retrieval. I think everyone now sees the potential of interactive large language models for finding information. So I tried this with ChatGPT to ask why is lab 42 in the example of lab 42. I don't know if the answer is correct though, because there's no source of the answer given here. Does anyone know if the answer is correct? Any clue, the people working here, Mohammed? Do you know if this answer is correct? The second part, I think, is quite likely. The first part, not sure. The 402. So no one knows, right? So here is already something that we as IR people have questions about, like how can we verify that this information is correct? So what we will do today, I have a very brief recap of Monday's lecture on transformers. And then I go into the opportunities and challenges of large language models in the information retrieval context. I will then go into two sides of the same coin. How can IR help LLMs to overcome those challenges? And the other way around, how can LLMs help IR? And in the lecture after me, Guido is going to follow up with, I think, a related and more advanced lecture about generative IR. Right, so a recap of Monday's lecture. I received the slides. Also, I cannot be here on Monday, but I received the slides from Christoph. And I think he covered all of these topics. Is there anything here that you think, no, this is new to me, we haven't seen this before? No, so I have two very quick quiz questions to see what you took away there. So here is a true or false, so let's do a vote. The self-attention mechanism in transformer models has quadratic complexity relative to the input length. So take a second to parse that statement. So let's do a vote. Who thinks this is true? Okay, who thinks it's false? And the rest doesn't know. So in my master lectures, I always do this kind of quizzes, and I tell students, you always have to vote, because forcing yourself to give an answer helps you think about it better. It's completely okay if you give the wrong answer, because we're exercising, we're still learning, but you always have to give an answer. In fact, this statement is true. So this image comes from Christoph's slides, where it shows that the self-attention mechanism in transformer models actually computes a relation, specifically the dot product, between each of the input tokens, right? And here it's between German and English, but in self-attention can be like the same tokens are on the horizontal and the vertical axis, vertical and horizontal axis. Right, so this quadratic complexity relative to the input length, which means that if we get longer inputs, this is quite a heavy burden on the GPU memory to process text by transformer models. And this is also why the original BERT models were limited to 512 tokens as input length, because more than that is very heavy to compute. Right? Is that clear? The notion of self-attention. Okay, then another quiz question. So this is an open question. So you have seen this. The original transformer is an encoder-decoder model. With on the left side here, the encoder, and on the right side here, the decoder. So here's a question. Can you name a transformer model that is encoder only? So only the left side here. Yeah.
BERT.
Yeah. So that was inquire BERT indeed. BERT is an encoder only transformer. And the E actually stands for encoder, right? So BERT only as this, it doesn't generate text. It processes text and then outputs a representation of that text. Then the other way around, can you name a decoder only transformer? So a transformer model that only has the right side.
T5.
Oh, someone said T5. Who said T5?
Yeah.
Do you think? Yeah, indeed. T5 is an encoder decoder. It has actually, that was my bonus question. So does anyone of you know T5? T5 has both encoder and decoder. But the most people called out GPT, and indeed, GPT is a generative transformer. It doesn't have an encoder. It only takes a prompt and then continues that prompt, the decoder side. So that was to awake you to very quick quiz questions about transformers. And let me now briefly introduce large language models. So as I said, GPT, a generative pre-trained transformer, is a decoder-only transformer. It was proposed in 2018, the same year as BERT. So the year after the famous Fatwani paper was published, in which the transformer encoder-decoder was introduced, these two models were also proposed, like an encoder-only and a decoder-only. And at first, BERT was way more popular because at that point, there were way more opportunities for encoder models because you could fine-tune them for labeling tasks, classification, extraction, like any supervised task. So in the first year, if you look at the citations of those articles, the BERT paper was incredibly popular. Like all of the research used BERT models. Whereas GPT as a generative model, yes, it could generate very fluent text. Some of you still maybe have worked with GPT-2 in their master. At least I did a couple of years ago. We worked with GPT-2, we fine-tuned it. It was already quite fluent. And it generates the most probable text. But at that point, that didn't have that many applications. But when these decoder-only models grow larger, they can do much more than only generate text word by word. And GPT 3.5 with 175 billion parameters, so that is huge, was the first model that became famous and well-known to the audience, as you know, in 2022, when OpenAI created a user interface to ChatGPT, which is a version of GPT 3.5 fine-tuned for conversation, for dialogues. And this, I think, was the start of the LLM era. But it's important to realize that the moment that GPT-3 became very large and researchers discovered that it could do way more than just generating text, was in 2020. So this paper, some of you, so who of you know this paper? Language models are future learners. Who has seen that before? Okay. So this was the first paper where it was actually introduced that when a decoder-only model becomes very large, it can do very cool stuff like following instructions and like doing few-shot learning with only a few examples. But in 2022, this really took off. And the interesting thing about this like increase in decoder-only models, increasing size, is that they start to are having much more capabilities than the smaller models. So GPT-2, as I just said, you could fine-tune it for tasks. So for example, we fine-tuned GPT-2 on empathetic dialogues, and then it became very empathetic. But it forgot real-world knowledge, right? So you could fine-tune these earlier models to do a task, but that was then what they did and no other things. But when the models become much larger, some abilities emerge. And this is a very interesting paper here. So another question, who knows this paper? Emergent abilities of large language models, who has seen that? Yeah, some are very convincing. Yes, yes, I'm a fan of that paper, right? So this is interesting. So there it was shown that quite suddenly, when you increase the number of parameters, the model has certain capabilities that the smaller models didn't have. This is what we call emergent abilities. And these emergent abilities actually led to a whole range of new opportunities, because these larger models, and especially when fine-tuned for conversation, are capable of following instructions and following up on some examples. So this gave rise to the opportunities of in-context learning, which is learning from instructions and examples given in a prompt, instead of thousands of examples to fine-tune a model, a BERT or GPT-2 model. Right, so zero shot in this setting means we only give instructions, and few shot means we give a few examples, and few is typically 2 to 5. If you look at papers, it's hardly 10. It already increases the context size a lot. So typically it goes up to 5. So to give an example, this is something I copied from a master thesis, where a student gave LLMs, several LLMs, an instruction to answer a legal question in English. And so interestingly, over time, the research community started to discover how to properly give these instructions. And I'm not going into that today, but there's a lot of work on how can we make the language model give better answers by asking it to think thoroughly or step by step, etc. But giving very explicit instructions, how you would also do it to a human, right? So in the past with human annotations, you would say, here's an annotation manual, please follow this very carefully and then produce your output. Well, that is what we now do also with LLMs. Right, so that's in-context learning. And this actually has led to a paradigm shift in natural language processing. So in 2018, 2019, the whole field moved to the use of transformer encoders, BERT models. We fine-tune BERT models. But when fine-tuning BERT models, we still need quite a lot of label data, like similar in amounts as when we in the past had feature-based models, like word-based classifiers and static embeddings-based sequential models. So we need a couple of thousand examples. So I have here much more than 100. So let's say at least 100 per category, something like that. It's just a ballpark figure. And we do this with an encoder model or an encoder-decoder, like T5 or BART, like for summarization, for example, Pegasus. We cannot give these models any instructions. We only give examples, the training data, and the model is actually being updated. So we fine-tune the model, and then we have a new model. And this model, we can publish again on Hugging Face. If you go to Hugging Face, you go to models, there are now tens of thousands, I want to say, but I didn't check this morning. I don't know, it is already hundreds of thousands, I'm not sure. But the amount of models there is amazing, right? So unfortunately, there is a lot of focus on English and news domain, and many of these models have been trained on the same set of data sets, etc. But you could train a model, say, for sentiment analysis in financial Chinese news. And then you publish that model again on Hugging Face, and then anyone else could use that model again to do sentiment analysis for Chinese financial news. But now, with the largest decoder models that we now have, the LLMs, we can do in-context learning. And now we only need fewer than 10 examples, let's say 5. We provide instructions to the model, as I just showed. The model is not being updated. So what is learned is of temporary nature. So that means that if someone else wants to do it again, they copy your instructions and they get similar output. Right, and this is a paradigm shift that we are really in the middle of. So right now we do both. If we, for a task, have a lot of label data, we still fine-tune models, If we don't have label data, we can use instruction tuning in context learning with a few examples. Also, if the task is very well defined, so we know what the label set is, and the label space is not incredibly huge, and the labels are clear, and we have the data, fine-tuning a BERT model is typically better than using in context learning with an LLM. So if you have the labels for some named entity recognition task, probably works better. But for a task that is new where you don't have any label data, in context learning seems to be a very good alternative. So yeah, we are right now in the middle of the shift and we do both. Any questions at this point? Okay, so let's quickly raise hands. So who of you is fine-tuning BERT models in their work? Yeah. And who of you is doing in context learning in their work? Yeah. So these are partly overlapping people, right? But not completely. Some people only do one of those. Right. So see, we are doing both. We as a field are doing both. So let me give an example. And it's nice that the person who did this work is actually here. So this was work of a master's student, Pavlos. He's in the room. And I typically give this work as example in my talks and lectures because it was a very early example. So when Pavlos did this work, it was the semester when ChatGPT was launched. So he started his literature review, he implemented his baselines, he fine-tuned the encoder-decoder models, etc. And then when ChatGPT was launched, he started using that as a comparison. So immediately jumped on the train. And it was quite a nice result. So what he did, he instructed GPT 3.5 to give summaries of scientific papers. Actually, this was a case of extreme summarization. So it was a really large collection of scientific papers published in a conference, and then summarizing it in one blog post. But that had multiple steps, like describe a paper in one sentence, describe a group of papers, a cluster of papers in one paragraph, etc. So he compared this to fine-tuned encoder-decoder models, so typical summarization models. So here they are, like CATS, Pegasus, and T5, and they were trained on a dataset, benchmark set called Sci-TLDR. And these are typical evaluation metrics for summarization. I don't go in there. There's lots of issues with them. Actually, if you work on summarization, you know that. But still, we use them as a comparison. But then, so these models were trained on 5,000 training items. Then if you compare that to GPT 3.5 in a zero-shot setting, it got to the same level, like without any examples, only instructions, it got the same level of performance as the fine-tuned models with 5,000 examples. And when you give it 2 examples, it actually increases over those settings. So this shows really the opportunities of these models to do tasks like summarization. So as I said, for things like extraction and classification, it's way more difficult to beat fine-tuned models. But for summarization, it's pretty good. Right. So that's the good news. Now let's go into some of the challenges that we have with LLMs. And the main challenge, if you think about information retrieval and search, is that the models tend to hallucinate because they are probabilistic. They generate the most probable word at each step in the generation. And because this is probabilistic, the output is fluent and plausible, but not necessarily correct. And this is more prevalent in low frequent topics and things that are very specific or local. And here I asked, what lecture did Einstein give in the summer school in Amsterdam in 1920? Well, at least Einstein was alive in 1920, and around that time he also visited the Netherlands, but there was no summer school and there was even no presentation of Einstein in Amsterdam in that time. If you ask that, ChatGPT, so this is very recent, so this is also the 4.0, of which people say, well, oh, that's much better and there's much less problems. And I agree, it has fewer problems than GPT 3.5, but still, it really struggles and it makes up a story here that's completely wrong. So I corrected, are you sure? I don't think there was a summer school in Amsterdam in 1920. And then, of course, it apologizes to me and it makes up another story, right? So this is a problem because we cannot check whether it's true. There is no source there. We have to go to a search engine to find out what happened. And actually, this is very common. So here are some publications from last year, but there's a lot of research going on hallucination and when it occurs and how you can present it with good prompting, etc. But one of the problems is, for example, in healthcare information, there is a lot of misinformation in the output of LLMs. So this is potentially an issue. Another issue is that these models exaggerate the bias that is present in humans and in human text. So we naturally, as humans, we have biases because we also view the world probabilistically. And so we more easily associate the term professor or doctor with a male than with a female person. Right? So we all have those biases. And the problem is that LLMs actually copy those biases and make them worse. So if you ask ChatGPT to write a text about a doctor and a nurse, the doctor will always be male and the nurse will be female. And yeah, even worse than that, the anecdotes that you get are quite stereotypical. So you can try this out. I must say, these kind of bias things seem to improve over time in ChatGPT. And I suspect OpenAI that they have some like classifiers or even rules to fix this, right? So like if you ask very explicit questions about ambiguous sentences, that has been solved in the past months. There it can say, no, it's ambiguous. It can be both male and female, right? But still, if you don't ask explicitly, but just ask to tell a story, then it will always fall into this probabilistic trap. The question, is that bad? Well, of course, it's not bad that if I generate one story, the nurse is female and the doctor is male, but it is a problem if it's always the case. And especially when humans are using large language models as suggestions for their own texts, or if companies are using these models for making assessments, making judgments. And yes, companies are doing this, right? So if you are using these models to judge CVs, for example, yeah, this really has strong ethical implications. On the other hand, I know there are also companies who say, well, we want to use these models because we want to get rid of human biases, right? So the models might have biases, but humans have as well. And by combining them in a smart way, we can get rid of biased decisions. And maybe that makes sense, right? So I'm not opposing the use of LLMs in general, but I just say you have to be really careful and conscious what you do with it. So speaking of ethical issues, there's some other issues you probably noticed, but also from your own experience, when you're training or using these models, it costs a lot of GPU energy. And another thing is that this was found, this is already relatively old, like a year ago or so, that the cheap labor of crowd workers was used to train ChatGPT. So to look at hate speech in the output and classify that as not okay. So the toxicity of that output is problematic to the workers, but also low payment, of course. So OpenAI had some negative press about this. So I think this is also relevant to consider. Good. So now I've presented those problems, also the opportunities, but also the problems with LLMs. And I would like to go into how can information retrieval help LLMs? And as an information retrieval person, I'm happy with this. And I'm also happy to see that the NLP community is kind of embracing retrieval now, much more than it did in the past 20 years, I would say. So the good thing about information retrieval is that search engines actually allow us to check the source of the information. So here's checking Albert Einstein in Amsterdam in 1920. I investigated this page and found out there was no visit, right? So yeah, this helps. We can judge whether the source is reliable. So nowadays, it's a good idea, and many people are doing this, to add sources to the LLM, not only for the human to check the sources, but also because the LLM is pre-trained on data until a certain date. And it doesn't have information from after that date. It also doesn't have information from, let's say, company internal documents. So if you want to use an LLM for information finding, for question answering, this limits the questions that can be answered. So the solution to that is to first retrieve relevant documents, add them to the prompt, and then generate a response. And this is called, Retrieval Augmented Generation, RAG. I think many, so who of you is working on RAG technology? Okay, quite some people. So I think many people are now looking into this. So this is how it works. We have a user posing a question to an interface, let's say an LLM interface. Then it first retrieves potentially relevant documents. It gives the question together with the list of relevant documents to the prompt, and then the LLM generates the answer based on this information. And if you read the example that I showed in the beginning of a prompt given by a master's student about legal question answering, she actually explains to the LLM, look, here's some documents ranked with BM25. They are not necessarily all relevant, but some of them might be relevant. And please base your answer on them and then reference them. And this works quite well, but you have to say something like, you have to give in your instructions information that the retrieved documents are not necessarily all relevant. So the LLM can then judge the relevance of the documents to the questions. It's quite interesting, I think. And that also makes BM25 valuable because that is lexical retrieval, where the LLM is doing semantic assessment. So this adds transparency to the reply of the chatbot. And actually, ChatGPT now has RAG for some types of questions. So if you ask it to write a biography of a non-famous person, it's first going to retrieve information about that person from the web and then generates the biography. That's quite nice. And also when I tried who's the organizer of ESSIR 2024, it's performing retrieval. So it enters this query, and then it retrieves actually the website of ESSIR. To be honest, I was surprised with the answer then. So is this actually true, Mohammed? Is Alice the organizer of yes. Okay. So I didn't know. So yeah, but at least now I can click here and check to see if the answer is correct. So I think this is very valuable. Right, so to summarize these advantages, is RAG allows the LLM to connect to the source for the human user to check the transparency, to enable retrieval from proprietary databases, but also to update the retrieval index without updating the LLM, like for new and recent documents, and adapt to a new domain without updating the LLM. Then some of the challenges. Who has experience with problems with RAG? I see in my work two main challenges. Who wants to say? Oh, yeah, I see it. Yeah.
So I guess it depends on how to do retrieval. So for example, if the popular way to do that is to do like embedding based. I guess the problem of that in practice is it cannot give you the exact documents you want. Because, for example, in some financial domain, right, all the text chunks are very similar, semantically similar.
Right.
You like the query contains some exact condition like time, and the embedding cannot tell the difference between like this year and the last year.
Yeah. So yeah, exactly. Yeah. So specificity of the answer of the retrieval result is then a problem. Other issues that people have experienced? Yeah.
Okay, so I think one big issue with RAG is that unlikely to be able to jointly train your retriever and your generator, because we usually retriever is kind of some existing index which is updated, which is live, and keeping these two systems coordinated and keeping the distribution, basically training model on one distribution, go to production, calculate different distribution, and kind of you can mess up everything.
That's interesting. Okay.
There is very strong tension between fluency and correctness, so we can get fact and just say, okay, I extract a fact like Google, and that is correct, completely correct fact. But then LLM doesn't add anything on top, just your fluency. Or you can try to do fluency summarization, and then you get all these LLM problems with hallucination.
Right. Yeah, exactly. So the first thing I hadn't thought about, and it's also a bit more abstract. So yeah, interested to hear more later. But I think so. The chance of this first thing was mentioned there. Retrieval is not perfect, and especially in specific domains. And it's also difficult then to identify for the LLM that there is no perfect information there. And hallucination can still happen. And we have recently seen, so actually next lecture more about RAG, but we've recently seen the problem of hallucination where questions have a wrong premise. So in the end of May, a couple of weeks ago, Google had some bad press with examples like these. How many rocks should I eat each day? So the premise about eating rocks is already wrong. But, well, you know, a search engine can find some information on any topic, so also about eating rocks. And it apparently found some sources and then generates an answer. And one thing that one of my PhD students found is that actually it becomes worse by hallucination. So it's not only repeating wrong information from wrong sources, but it then makes it worse by hallucinating over that. Right. So it seems that, but yeah, we're still looking into that. It seems that hallucination becomes worse if the sources are poor and if the question has incorrect premises. So here are things that need attention. Actually, my IR research exam next week, I have a question about like, what would you advise Google to do to prevent this kind of thing? So I think for RAG, they need to pre-select domains or documents automatically that are reliable, right? So Reddit or The Onion is not reliable for this information. Good. Any remaining questions or comments about RAG? Yeah?
What do you do with latency?
Sorry, what?
What do you do with the latency? Because the latency is compounded.
The latency, like the time the user has to wait for getting yeah, it's a good point. I actually get to that also next, and like the trade-off between retrieval and generation. Retrieval is typically much faster. Yeah, true. So I mean, it's an interesting question because somehow if you go to ChatGPT, the answer is generated seemingly word by word. So they do that, of course, visually also to make people wait. Yeah, exactly. Yeah, so I think, yeah.
Depending on the scale of retrieval, sometimes retrieval can be slower.
It depends on your, yeah, okay. It depends on your model, it depends on your index. And if you have an efficient implementation of BEAM25, like in like Elasticsearch, it's really fast. It's really fast.
Yeah.
But indeed, vector databases and dense retrieval can potentially be slower. Yeah.
Yeah.
Yeah, but actually, I would like, or yeah, by default, I would advise the use of BEAM25 in RAG because the LLM can do the semantic assessment of relevance, right? So dense retrieval is embedding space like LLM. And BEAM25 gives you the lexical retrieval results, and then the LLM can do.
But to that point, why not do generation? Every time the coding, you just ground the
yeah.
That is the same thing that you are doing. You are just
constraining the retrieval side and constraining the retrieval.
Yeah, I agree. Good idea. Yeah. Right. So still lots of things to do here. Okay. So so before the lecture, there's another topic that I want to introduce, and there is a lecture tomorrow about this topic in more detail. But I think conversational search is a domain or a task where LLMs and IR are quite closely together. So there is a book from 2022 by Hamed Samani. It's called Conversational Information Seeking. Unfortunately, the book was outdated the moment it was published because it kind of predated ChatGPT. So yeah, the concepts from the book are still valid, but technically, methodologically, it's outdated. So in that book, it's defined a conversational search system is defined as a chatbot with information retrieval capabilities. So here again, a short conversation with ChatGPT about Einstein. So what do you think? Does a generative LLM have information retrieval capabilities? I'm not talking about RAG, but just the generative model. Does it have retrieval capabilities? What's your opinion? Yeah.
We define retrieval.
Yeah, good. Yeah. What do you want to say?
I would say it's kind of like underlying capabilities that the model have to do in order to predict.
Yeah.
So yes.
In a way, yes. Okay. Yeah.
I think there was a study 1 or 2 years ago that NLP layers basically act as key value stores, and that the model can retrieve information from the NLP layers.
Okay, interesting.
So in that sense, yes.
In that sense, okay, good. Yeah. So indeed, so if you look at literature about models, like they sometimes use the word retrieve to refer to like getting information from the layers. Yeah, good point. So I saw Mohammed nodding, shaking his head. So strictly speaking, no, because no information is retrieved from an index, but it does provide functionality for information search. So I think the word search now became broader than retrieval, right? But it's a matter of definition, and I agree with Sean. Please define information retrieval. And in a way, so it has also been shown that LLMs tend to memorize some things from their pre-training data. And it can retrieve them and you prompt them in the right way. So there's work on that in the context of privacy and security, which is also interesting. I'm not referring to that necessarily. Right. So if we think about, so here's like a chatbot with information retrieval capabilities. So the approaches to conversational search are, on the one hand, retrieval-based approaches. So get the best possible response from a collection of previous responses. Generation-based approaches, which is generate a response in natural language. So this is completely like the ChatGPT approach. Or hybrid, first retrieve information, then generate a response. That's RAG, as we just discussed. Or there is this option where, in principle, you get the best response, but if there is none, or the information has to come from multiple documents, then you aggregate and generate the response. So their generation becomes a fallback option if there is no one clear answer to a question. So this is also a hybrid way. And each of them has pros and cons. So like in retrieval-based approaches, the source is always transparent. We know that we literally get information that is there in the index, so there's no hallucination. It's typically efficient, given that you use good implementation of a good ranker, of a fast ranker. And the evaluation is rather straightforward because your benchmark set consists of the correct answer. On the other hand, the answer space is limited, which means you cannot give any answer that is not in the collection, right? For some domains, like think about help desks, right? What if someone asks a question that hasn't been asked before, right? It's difficult. It's potentially not very fluent and it's less interactive. And then if you look at the generation-based approach, it's exactly the opposite. So it's fluent, it's tailored to the user and the input. So I would say it's very user-friendly. And this is also why people like interacting with chatbots. But on the other hand, there's the risk of false information due to hallucination, and it's GPU heavy, and the evaluation is more challenging. So I think yesterday or the day before, did you have a lecture about evaluation metrics in IR? Right, you had, right? So you know that for retrieval-based methods, you need a benchmark collection, test collection that has queries, documents, and relevance assessments. This is exactly the same in the conversational context. So there's, for example, the Stack Overflow data set. There is a question, a set of responses, and there is voting for the best response. And this is then used as relevance assessment. And we can compute the typical IR metrics like precision and MRR. There's only one correct answer. But on the other hand, for generation-based methods, this is challenging. I already mentioned that in the context of summarization. Summarization is actually the field where the typical metrics for generative question answering and generative conversational search come from. So what you see in these papers is that they apply a large suite of methods. So they have a whole, like a very broad table with like 8 different metrics to get a global view of the performance of the models. Because none of these metrics alone is giving the whole picture. So these 3 ones are based on word overlap. So this is literally, we have a correct answer by a human, and we have to generate that answer, just count how many words are overlapping between them. You can imagine there are many different ways to give the same answer, that this is a very poor proxy of evaluation. Then there's word score, which gives semantic similarities, already a bit more flexible, but still the answer can be completely wrong and still very similar semantically, right? But because one word not is making a big difference and not really changing the word score much. And then there is this interesting approach where you customize your own metric in an LLM. So there's this paper called GEVAL, and there they use GPT-4, but we also use Llama 3 now for that. So you basically instruct an LLM to look at specific aspects of the answer and evaluate them. So you have to make very clear instructions. And you could then define, let's say, 5 different metrics to evaluate the answer. I think it's interesting to do this. Although I also sometimes think about this meme where you have the Spider-Mans pointing at each other, right? Do you know what I mean? Because I mean, evaluating one LLM with another LLM, sometimes even the same LLM, it can be a bit questionable. But then again, you could consider a well-instructed LLM to be an agent to perform one specific task very well. So you can instruct an LLM for one specific metric, and it can do that, right? So keep thinking about the Spider-Mans, but still pragmatically also use these methods. You still need a set of questions and human formulated answers as a reference. Okay, let's take a break here. Let's stretch our legs, it's healthy, and get some coffee. I also want some tea. And let's be back at 10 for the second half of the lecture. I see. So there's comment in the chat that the sound of the audience is not heard. I should remind of repeating what is being said. Yeah. Thanks. Okay. So to summarize, challenges of generative conversational agents and conversational search systems, hallucination, but there's also a thing with self-consistency, like to what extent does the models stick to the same story and the same concepts. And then there are issues with safety, toxicity, controllability, transparency. It's difficult to control the output of a generative model. And finally, yeah, the high memory burden for training and utilizing these models. And then definitely in some domains, it's preferable to use retrieval over generation. So here's an example. I was already mentioning the health domain. And actually, I regularly give talks to medical researchers and doctors. And many of them actually use ChatGPT nowadays, which is I think, okay-ish, as long as they use their expert glasses to interpret the output. So there are some examples I've heard where people said, okay, I use it for brainstorming in difficult diagnosis, and it gives me some ideas. And then in the end, it's the expert who draws the decision. However, when patients are using these models, it can be problematic. And there was some news in the past where patients were supposedly more happy with the output of ChatGPT than with the output of a medical professional. But I want to say there, like, user satisfaction is not necessarily the same as correctness, right? So keep that in mind when you're evaluating something. What do you want to evaluate? Do you want the answer to be correct? Then don't simply ask users, are you happy with the interaction? So here's another example. So in the medical domain, this was medical question answering for person, where a student worked on answer retrieval. Actually, very challenging. This is one of those rare tasks where the answer is shorter than the question, typically. So doctors give very short answers. Another example is legal question answering. This is an American website where people can ask questions to lawyers. So expertise is relevant, and you cannot just hallucinate something that is plausible, right? It has to be legally correct. Okay. So more about conversational search tomorrow. And now let's go to the other side of the coin, which is how can LLMs help IR? So I want to go into several tasks here and topics: query and document expansion and data augmentation. So sometimes, as I just introduced, it can be risky to use generative models in direct interaction with a customer or a patient. There might be non-factual output there. And if you think about service chatbots like companies have, so you probably know, if you live in the Netherlands, you know chatbot Billy from bol.com, a large online retailer. The company doesn't want the bot to generate something that is not true, right? So like you can send something back after you used it, and you can send something back after 3 years and get your payment refunded, things like that. So it's very important that the information is correct. So in general, it's considered more trustworthy by these companies to use a retrieval model to find the relevant information and then refer the user to that. But we can still use LLMs, and companies are doing that, to actually augment the training data. So the source collection or the training data the retriever is trained on. So let me go into that. And this is all work that was introduced a couple of years ago. So in the time that we had encoder, decoder transformers, but it wasn't yet the time of the generative large language models yet. So here's one problem that we have in retrieval, which is called the vocabulary gap. So a query might be bike lanes, where a relevant document is about bicycle lanes, and here's a nice Dutch picture of a bicycle lane. It's exactly the same thing, but the words are different. So we could say in the IR approach that we could expand the query bike lanes with the word bicycle, which is a synonym for bike, and then we can better match and find texts that are about bicycle lanes. Or the other way around, we can expand the document on bicycle lanes with the term bike and then better match the query bike lanes. Both are valid options, both have advantages and disadvantages. So query expansion can be implemented in a live search engine. No changes to the index are needed. So this is relatively flexible. On the other hand, document expansion is convenient. You can do it at index time, so it doesn't place a burden on the latency for the user to wait for something. So both is often used. And I now want to describe one. Oh, by the way, I didn't mention it, but it was on the slide. There is an excellent online free book from Jimmy Lin et al. It's called Transformers for Text Ranking, BERT and Beyond. It's from 2021, so it's a little bit older. But still, I think it's very good in introducing many concepts that are still very relevant. So these slides are based on that. So the technique that I want to discuss here that is quite successful and commonly used is called doc2query. Doc2query is a technique for document expansion. And the idea is that we train a sequence-to-sequence model on data of which we know the documents are relevant to the query. So we take a document and we take a query for which we know the document is relevant, and we teach a sequence-to-sequence model to generate a query from the document, right? So given a document, generate queries for which the document is relevant. So kind of reverse search, that's how we train a model. And then we use this on documents in our collection to generate potential queries, can be multiple. And because the sequence-to-sequence model is also generating non-literal words from the text, we can like get expansion with synonyms, etc. So we append these predicted queries to the original document. So in the example of bicycle lanes, we have this document about bicycle lanes, we ask the model, generate some possible queries from this text, and it might come up with the query bike lanes. We add that to the document when we index it, and we have more possible lexical matches. So this was in a later version done with T5, which makes complete sense. T5 is a very powerful text-to-text transformer, and it's very flexible, so you can use it for translation, for summarization, etc. And so also for query, document-to-query generation. So this is a very nice short report on this that you can read. It's very intuitive. So how does it work? Well, upon training, we have a text collection with relevance assessments. So for example, MS Marco, we know which documents are relevant for each queries. We generate queries, we append them to the documents, and they are indexed. And then, and here comes the trick why this is so powerful, the retrieval is done with BM25. So why can we do lexical retrieval now? Why don't we need any dense retrieval anymore? Yeah?
Because we have solved the vocabulary gap problem.
Yes, the answer is we've solved the vocabulary gap problem. Yes, a bit more exact. So why do we not need transformer-based embeddings anymore at query time? Any idea? Why does this help lexical retrieval? Yeah, okay. So we used a transformer generator to add more lexical matches to the document. So yeah, part of the answer is correct. So at index time, we did the semantic part of the matching. At query time, we don't need to do that anymore. So this makes lexical matching have access to the output of semantic models. Here's an example from this paper. So here is a text about July is the hottest month in Washington, D.C. So we are going to Washington, D.C. So who of you is going to Washington, D.C. in 2 weeks? Right, there is a SIR conference there. So good to know it's the hottest month in Washington, D.C. with average temperature of 27 degrees. So the target query here, that is truly from the collection, what is the temperature in Washington? And this is queries that were generated by these doc2query models. And interestingly, the model does produce some, when trained properly, does produce some queries that contain terms from the document, but it also produces some terms that are not in the document, but are semantically related, like weather, right? So, So this means that the semantic matching has been done at index time, right? Is that clear? Because, yeah, just before you are still not sure, but now, okay, semantic matching has been done at index time. We don't need that. And that means we can do lexical matching. And this is interesting because now, if you compare, so this is a large result table, but let's point out the relevant stuff here. So this is the BM25 baseline, and as you see, it's quite poor. And then on the other end of the spectrum, there is the Bird's large re-ranker, which is way, way better. But then if you look at these like doc-T5 query, then okay, it doesn't lead to the scores of Bird large, but it has a very good recall here, even better. So recall becomes very high, and see how incredibly fast it is. So latency, because we are using a lexical ranker here, latency is very, very fast. Right, so very, very low, and the retrieval speed is very fast. So compared to having a cross-encoder re-ranker. So this is a really efficient way of a strategy that you can do at index time to close the vocabulary gap with semantic matching. So that is one way how we can use LLMs like T5 when properly pre-trained. So T5, by the way, also comes in several sizes. So there's T5 base, T5 small, T5 large. And these are very powerful sequence-to-sequence models. So we can use them at index time and then improve retrieval quality. Is that clear? Okay. Then we go to the other option that we have of using LLMs to help retrieval, and that is data augmentation. So let me motivate this with another image from the same book, Pre-trained Transformers for Text Ranking. This is an image that shows how many training examples are needed to train a good ranker. So here, BM25 here, so this is on MS Marco, MRR at 10. BM25 is not trained. So there's just one dotted line here indicating the MRR of BM25. And here you see that for Bird base to become better than BM25, you need a lot of training examples, right? So a couple of thousands before you cross it. So for domains where we don't have that, and this is quite common, think about legal IR, we don't have thousands of query document paired relevance assessments. So that means that we're not better than BM25. And this is indeed, so you might have experienced this, right? So you did an effort to train a good re-ranker, and you cannot beat your BM25 baseline. This happens in many domains. So it's not you, it's the data, right? So if we want to have a more powerful ranker, we need more training data. And in many domain-specific settings, we don't have that training data. So what we ask is, can we create synthetic labeled data with generative large language models? And then ask the question, so investigate, to what extent does the synthetic data resemble the real data? But more importantly, what is the quality of a model trained on synthetic data when evaluated on real data? So this is an important point. If you want to measure the utility of your synthetic data, always evaluate it on real data. So take the real test set and make a fair comparison between real training data from humans and synthetic training data on the same test. So I think an important aspect here to mention is that when we use synthetic data to train models, we don't really have the risk of hallucination when showing output to humans, because we still train a retrieval model and we get information from the source. And hallucination might have an effect in the training stage, but it can never be as severe as when directly using the LLM for generating the answer. So I think this is a great way of using the power of generative large language models in the context of IR. So what options do we have? We can generate queries as training data. We can generate documents. We can generate relevance assessments, although the community has some discussion about that, whether or not we should do that. Or in the conversational context, we could say, okay, let's create some user utterances for known labels that we have. So let me show an example of this. So this was a paper from one of my students where he used an LLM to generate synthetic documents for queries. So he had questions, I think was it from the natural question data sets? I think so. And then ask the LLM, answer this question. There was no extensive prompting at that stage, it was just answering the question. So we create synthetic documents like that, actually passages. That in itself was relatively low quality, so we then filtered based on a post-processing step, and then we trained the re-ranker on the filtered data. But it becomes more interesting if you use the LLM also to improve its own data. So here is an example. Here was a query. Converting stereo signal to mono signal is cold. So this is a bit noisy. If you give this to the LLM, it will not create a good document. But then if you first ask the LLM, can you make this into a proper question? It already improves a bit, but it's still not great. But then, and this was a very interesting and creative step, what the student tried is ask the LLM to highlight the most important terms. And he tried several options here. He tried quoting, curly brackets, square brackets, different kinds of things. And in the end, the square brackets were the most effective. So this was all being done by the LLM. So again, here we use the LLM with different instructions for different tasks. So we basically have multiple agents in place to improve our data. And then we say, okay, now we have a clearly marked and well-formulated question. Now we ask the LLM to generate the answer. And now we have a good answer that we can use as training data. So each of these steps was actually few-step learning. So we gave 3 good examples, hand-selected examples of what we wanted the model to do. Right, so that is also how you can achieve that it's doing this in the output. Is this clear? Are there questions about this? So what do you think? Will this lead to a data set that's good enough to train a ranker? So we can do several things, right? We can use this to replace the human data, but we can also use it to increase the human data. And as we all know, more training data will lead to better results, even if the data that we have is partly noisy, because of course this data is noisy. Of course, human data is also noisy. So this is what we try, what the results show. So with different re-rankers and with different types of data augmenters, so this is like using import, so this is the query generation, and then there are some other baselines, query development generate, and then our method on several data sets. So here's natural questions, Marco, Hotbox QA, Fever, and this is if you only have human annotations. So as you see here, the human annotations is always still better, right? But if you combine that's in a different type, that's something, if you combine the data, you can get an increase. So this is how data augmentation can actually give you more data to train your models on and still have a reliable ranker. One interesting thing that I want to add here is that actually this was less good for more specific domains. So we tried this also for legal questions and for medical questions. And then actually the result was rather weak. So that means that data being generated for those domains is still less good. So maybe now with GPT-4o it's better because this is a paper from last year. At that point, LLMs were not good enough yet to generate data for those domains. Right, so that relates back to my point about legal and health information retrieval and question answering, where I think you should not replace the human expert with an LLM. Okay, I have another example, and this is very recent work of a student who's also here, Ivan. And this is, so here again is the picture of Billy, the chatbot. And so interestingly, we as a scientific field, we work on retrieval methods and we work on generation methods, we work on dialogue systems that are naturally interacting with the human, but companies actually have pipelines in place. They want to safeguard, they want to be sure that the chatbot is not going to generate something that is wrong. And so they have a whole set of tasks in their backend for classifying things. So they classify, for example, does the user want to be referred to a human? Is the user in any way frustrated? Is the user, like, when are users dropping out? What is the topic of the question? What is the intent of the question? So they have a whole set of classifiers in place to identify what the user wants. So this means that the task of intent detection, which in IR is a relatively old task, is actually very relevant nowadays for these companies. They even sometimes work with templated replies. So they classify what the user wants and then generate like a well-structured answer to be completely sure that nothing bad happens. So right now, all these companies, they do want to modernize their chatbot infrastructure. So we're working on that. But intent detection is a relevant topic for them. So if you think about service chatbots for large companies, they actually have to work in multiple domains. So for example, both banking and utility and travel and housing and I don't know. So we can come up with lots of different domains. And each of those domains, you can think of multiple tasks that the user wants to complete. So we call those intent. For example, in the banking domain, you could have I want to block my card, I want to freeze my account, I want to increase my limit, I want to change to worldwide setting, right? So these companies come up with a set of intents that users might have when they come to the chatbot. But for new domains, there is no labeled data. So they don't have actual user utterances with labels for these intents. And this requires data creation with a few items per intent category. And if you are, and this is one of the data sets we work with, actually has 15 intents for 10 domains. So having to create examples for each of these is a lot of work. So what we do is we use a generative large language model to generate utterances for us as training data. So here is a prompt. Give me 6 user utterances indicating the user intent of plug type in the travel context. So travel is the domain, plug type is the intent. And then we use LLM, like Zephyr or Llama, to generate some utterances. And actually those utterances are not great. They are also not terrible, but there's not a lot of diversity in the words that they use. They tend to repeat a lot the terms from the intent. They're not very suitable to replace human data. So what Ivan did, he actually trained a model to improve. So this is a T5 model that takes generated utterances and creates better utterances. And this is trained on a domain where we do have data. So maybe in the banking domain, we did have some data on like freeze my account, or in the utility domain. And then we apply it to an unseen domain and we get some utterances. And then we evaluate this for the utility of the generated data by training an intent classifier, just as I showed you for the ranker of the questions by generating answers. Right, is this clear? So here's some examples. So this is the domain of banking, and here the intent is freeze account, but there was no training data for this domain in this case. So the real data looks like this. Please freeze my account. I want to change account. I want to mean video. I want to block my change account. Meaning. Okay. Then if you ask zero shot to Llama 3, can you generate some utterances with the intent freeze account in the banking domain? It comes up with this. So as you see, it's way longer than the original ones. And it looks okay, but it's not too similar to this. But then after applying the refiner model that was trained not on this domain, right, on a domain where we have data, then we get way more realistic utterances of a user in a chatbot. And actually, this was quite successful and much better. So what you see, so 0gen is only using the LLM, and SuperGen is some prior state of the art. So as you see here with both Llama and Zephyr, we get a better result. However, when trained on real human data, the classifier is still way better. So there is a big gap here, bigger than in the retrieval task that I showed you before. So there is still a lot to gain there. But here as well, you can use the augmented data to add to the human data and have more training data and thereby get a better classifier if you have some human data. So this is using all of the human data. Questions about this case? Yeah.
I don't know what is there, but what is the classifier? Is it in,
The classifier is a distilled bird.
Oh, it's a bird as well?
Yeah, no, not as well.
What is the word?
Distilled bird.
Oh, distilled bird.
Yeah. Yeah, so that's just a regular supervised classifier. Yeah.
Do you know if you can do this? Because as far as I know, that you cannot use Llama outputs to anything downstream LLMs, including the.
Why not? You know, because of the license.
Yeah.
Ivan? I don't know, honestly. So he was saying that the Llama license does not allow to train a classifier on its output. I didn't know. No.
Is it published?
Not yet. No.
Okay.
So let's see if someone trips over that. But we do have also Zephyr, and we also now have the comparison.
I'm not sure about Zephyr, but
yeah,
what I landscape, most of the LLMs which are claimed to be open source, including Quen, you cannot do that.
Ah, right.
I think Mixtral, Apache 2, and some even Quen it says Apache 2, but if you go inside the license, you'll see it.
Yeah. So let me repeat for the online audience. It's a very good point made. I didn't know that.
Yeah.
So, but that's why on purpose do not use the word open to refer to Llama because it's not at all open. But right. So at least you can use it locally. So that's the distinction that I make. So there's commercial models that you have to approach through an API, like GPT 3.5, GPT 4, and there is like models that you can use locally from Hugging Face. Yeah.
Yeah, GPT you can actually, but I'm almost 100% sure.
Let's check that. I think it's very relevant. I didn't know that. Yeah. So did I repeat your question for you? I don't know. So he made the point that we, in the license of some models, including Llama, it's actually said that you cannot use the output of the model to train a classifier. Good. Thanks for that.
It can be a classifier.
Yeah. Okay. Good. So let's conclude. So Mohammed allowed me a couple of more minutes because I had to break in between. So in summary, I think these are academic goals. Yeah, you couldn't see, but I was actually pointed the sheet with the 5 minutes on it. So so I think it's important to, where possible, to use open models. So again, Llama is not really open. There's an interesting paper, by the way, on like ranking models by openness. Check that out. I could refer to it. It's interesting. I think it's very important that we work on models for less resource domains and less resource languages. Like in the bird era, which we're still partly in, but if you check for bird models, there's actually, for many different languages, there are bird models. But LLMs are so much more heavy to pre-train that almost everyone works with these same pre-trained models like Mistral. And for many languages, it's way poorer than for English. So I think it's very important that, and there are some initiatives now, at least also funded by the European Union for non-English LLMs. The development of models that are efficient in the use of computing resources and data. So I think that using quantized models, using the 7 billion version of models, you have to instruct them better, but you can run them on a much smaller GPU, which is also much more energy efficient. So I think that's a very important direction. And then focus on human aspects. So how can we help humans? How can we help desk employees? How can we assist them, not replace them? How can we assist lawyers and doctors, not replace them, right? So, and also in the evaluation, look at this multi-aspect evaluation, not asking humans, do you like this? But look at several aspects of the output. And finally, transparency. So IR remains important. And then a future aspect, and that's actually where the next lecture is also about, the idea of generating the document IDs of the index. So, you know, the IR task is we have an index, every document has an ID, and we have a query. And in the traditional IR setup, we look at the content of the query and the content of the documents and we match them. But what if we can do sequence-to-sequence learning to translate the query directly to the document ID? And it might be a strange idea, but I think this is the future. This paradigm is called generative IR, and I think classification is also going to be like this. So LLMs, generative models, are going to replace, in my view, encoder models and regular classifiers that you have to train. So I think there's some interesting early work on that, and there's more about that in the next lecture. I'm also interested to learn more, to actually generate the document ID and then get it from the index. So if you're curious, come back after the break. And on the last slide, I always have some learning goals where you can check if everything of this was properly explained to you. And I will also share my slides, put them in the Google Drive. So yeah, that concludes. Thank you for your attention.